forget to do that. And let me open up this exam. So on heat pumps, we already went through these slideshows, so hopefully you guys remember most of this stuff. I am going to just kind of go through the questions and talk about what's on each question. We're just going to do it like that, so hopefully you guys will be okay when you go to take the test. Remember how geothermal heat pumps work. Geothermal heat pumps work by transferring heat from the unit to the ground, right? So from the unit to the ground is how geothermal heat pumps operate. We're going to transfer our heat from our unit outside through tubing that is drilled or on a horizontal field to come through a big loop, usually a loop of PEX piping, right? And then it goes back to the unit and continues to circulate around it. So it's the same as a water source heat pump, except instead of a chiller and a boiler to send the heat off to either get the heat from or send the heat to, we're going to be using the earth, right? So that one doesn't require too much explanation. Just make sure you remember that. Geothermal heat pump transfers our heat that way. And as a side note, with geothermal or chillers and things like that, we tend to call that water in the system is kind of our secondary refrigerant, right? It's our secondary heat transfer medium. So that way we could probably just run the refrigerant piping through a big loop in the ground, but that would not be the best way of doing so in case we have to ever make repairs to any of those circuits. So we use water as a secondary refrigerant. Remember that word in case you ever happen to see it one day. Alright, defrost mode. You need to know defrost sequence of operation. So you should be very familiar with the sequence of operation in defrost mode. I believe, as a matter of fact, I can probably check real quick in Google Classroom in the class I set up for you guys. I have sequence of operations in there. So there should be a handout that I posted there on sequences of operation. Yep. And that's got a typical defrost mode sequence of operation in it. Matter of fact, I will pull it up real quick and just read through defrost real fast. That way we've covered it again. So, I think I got just defrost mode here, or is it part of heating? No, it's part of heating. So in the heating sequence of operation, you lost my audio? Okay. Alright, let me know if it cuts out again or something. So, defrost mode. Every 30-90 minutes, if the defrost thermostat is in the closed position, outdoor coil temperature is 32 degrees or less. And let me make a side note there real quick. Depending on the defrost thermostat in the system, it could operate in a normally closed or a normally open position. So just keep that in mind. That could be reversed. So, it might say if the defrost thermostat is open, or it could be that the defrost thermostat is closed. But either way, it closes or opens about the same areas here. It's just some defrost cycles are set up for a normally closed switch. Some defrost boards are set up for a normally open switch. But anyway, every 30-90 minutes, if a defrost thermostat is in the closed position, the outdoor coil temperature is 32 degrees or less, the system will enter a defrost cycle. Defrost control will power the reversing valve, and the refrigerant circuit will switch to cooling mode. Defrost control will de-energize the outdoor fan motor. Defrost control will send 24 volts to W powering electric heat. Defrost cycle will continue to the defrost thermostat opens at 60 degrees or until 10 minutes of time has elapsed. So the defrost cycle is going to terminate based on the temperature of the coil or based on how long it's been running, and then the unit will re-enter normal heating mode. Again, a defrost thermostat might be normally open or normally closed. That's something you'll have to determine based on that piece of equipment. And some equipment, instead of powering the reversing valve, it will remove power from the reversing valve, because some systems are set up for the reversing valve to be normally in heating, which is most of them, but some systems are set for the reversing valve to be normally in cooling, which is a small few of them. I think mainly just Rheem these days, but there could still be a couple manufacturers that use a B terminal instead of an O terminal. An O terminal is the most common one, where the reversing valve, if it's energized, moves into cooling. If it's got a B set up, then that would be the reversing valve energized in heating. But either way, you basically change the position of the reversing valve, de-energize the outdoor fan motor so that we bring the coil temperature up very high, switch the unit into cooling mode without the fan running, and then power the electric heat to minimize the impact on the space so that people don't feel the cold air while this unit's in cooling mode. And then it continues until the thermostat changes position at 60 degrees, or once 10 minutes have passed, if the coil still hasn't reached 60 degrees, defrost will terminate anyway. So defrost tends to terminate on time or temperature. Okay, time or temperature. In heating mode, the reversing valve will normally, as we just talked about, be normally de-energized. Alright, but again, some systems are the opposite, but for the purposes of most systems, you should remember that the reversing valve is normally de-energized in heating mode. In cooling mode, it's going to be the opposite, right? In cooling mode, the reversing valve will normally be energized. Again, this isn't the same for every system, and you need to know that particular system. But in general, that's how they operate, okay? And on your test, just to give you guys a heads up, on your test, those are the kind of things that they're going to ask you, and those should be the answers, okay? Even though that's not fully correct, and I don't agree with the fact that they ask those questions like that. I assume that's the way they wrote it in your book, but there are still plenty of systems out there that work opposite, so make sure you know that. Like I said, I know for a fact Rheems do. But most, I'd say probably 90% of them out there, those are the positions. Next one. What are they trying to say here? Give me just a second. Let me reference this answer real fast, make sure I tell you guys what they're doing. Oh, okay, never mind. I was about to say what? No. Okay. So, emergency heat on a heat pump. Emergency heat, if you have a thermostat, most thermostats for heat pump have an emergency heat feature. The emergency heat basically de-energizes the heat pump. It's there if there's a failure or an issue with the heat pump. That's what the setting is for. So if you put a thermostat into emergency heat, what will happen is only electric heat will operate. Everything else will operate normally. The fans will come, the indoor fan will come on, the electric heat will energize and everything, but it will not run the outdoor unit. That is what emergency heat is for. If you have a dual fuel system, then so that would be a heat pump with a gas furnace. Emergency heat will just bring on the gas furnace. It won't energize the heat pump. So it depends on the system you're working on, but for the majority of them that have supplemental electric heat, the electric heaters will run and the heat pump will not if you place that system into emergency heat. Remember that with heat pumps, so the next question you're going to have is going to be about operating modes and the state of your refrigerant. So again, I would highly suggest that you look at that sequence of operation that I have on there, because that should help you remember. But I don't show refrigerant circuits on that. I think, let me see if I got something on your all stuff. I should have a refrigerant cycle worksheet on there, I believe. Let me make sure. Let me make sure I got a refrigerant cycle worksheet up there for you guys. Got a troubleshooting guide. Okay, yeah, if you look through the troubleshooting guides, I got a system evaluation guide there. That is pretty good at looking at a sequence. It's not perfect, but that's pretty good. And there should be, I'll try and post the worksheet that has my version of that refrigeration troubleshooting guide on it. But anyway, remember that in a heat pump, the roles can get reversed, right? So normally your system is your system in cooling. The outdoor unit will have hot vapor at the beginning, and at the end have a subcooled liquid. And your indoor unit will have a subcooled liquid at the beginning and a superheated vapor at the end, right? In heating, it's going to be the opposite, because the indoor unit becomes your condenser. So you will have hot superheated vapor at the beginning of the indoor unit and subcooled liquid at the end of the coil in the indoor unit. And then at the beginning of the outdoor unit, you'll have a subcooled liquid, and at the end you'll have a superheated vapor. It just reverses what the indoor and outdoor unit do, which is why, especially with the heat pump, it's good to stay out of the habit of calling the outdoor unit a condenser and the indoor unit an evaporator, because that's not what they are. They can be either or. It depends the mode that they're in. So it's better to label them outdoor unit, indoor unit. So in cooling, the outdoor unit has hot high pressure vapor going in and a subcooled liquid going in on the indoor, and then that role reverses in heating. Okay, so that's how that is going to work. And remember that defrost is the same as a cooling cycle. Okay, so cooling and defrost have the same states of refrigerant because they're the exact same cycle. The only difference between cooling and defrost is that the outdoor fan motor is off and the electric heat is on. Those are the only two differences between cooling mode and defrost mode. Alright, so the outdoor unit's the condenser in cooling, the indoor unit's the evaporator in cooling. In heating, the indoor unit's the condenser and the outdoor unit's the evaporator. And defrost is the same as cooling, other than those two things I mentioned. And stop me if you have any questions, alright? Alright. With a dual fuel heat pump. Okay.
Somebody's in the waiting room.
Is there? It's been popping up.
Not too long ago.
Yeah, no, I think I got it. We got everybody in here now. We got all 7 of you. Yep. Okay. Okay. So with dual fuel, let me make sure I'm going to give you guys the right answer here. Make sure they're not throwing me for a loop. Okay, good. Alright. Dual fuel is interesting, right? Because the heat pump and the furnace cannot run at the same time. So typically dual fuel is going to be a propane or natural gas furnace with a heat pump over top. And it's more common with propane systems because propane's so expensive that you really want to save as much money as you can. All right? You want to save as much money as possible on propane during the winter. All right? But since you've got a furnace, and that furnace is below the coil, is one of the main reasons. There's a couple reasons, but just remember this as your main reason. Since the furnace is below the air conditioner coil, you can't really blow that 120 to 130 degree air from a furnace over the refrigerant coil when that refrigerant coil is going to be the condenser, okay? The air is way too hot. Remember, your normal operating temperatures for a condenser, ideally, is 75 to 95 degrees, the way we design systems. So that's our ideal temperature of air blowing across a condenser. Since in heating mode, the indoor unit is the condenser, you can't really blow 120 degree air across it because you're going to trip a high pressure switch or something. All right, it's just too hot. The air is just too hot to cool down a condenser. So the furnace only operates when it needs to. You have to set some kind of point where the heat pump goes off and the furnace comes on. And the thing is that's going to be different for every house. Okay, every single house or building for that matter is going to be different where you need to cut off the heat pump and turn on the furnace. That is because there's a heat pump puts out different amounts of heat based on outdoor temperature. So if it is 70 degrees outside, we can pick up a ton of heat from the outdoor air, right? Because it's 70 degrees outside, so there's plenty of heat for that outdoor unit to pick up and take inside. Remember, a heat pump picks up heat from the outside and takes it inside. Okay, so we're picking up heat from the outside air and we're giving off heat to the inside air. So, at 70 degrees, the heat pump can provide tons of heat, right? Just tons of it because it's plenty warm. But when it's 0 degrees outside, a lot of heat pumps can't barely pick up any heat at all because it's just so cold outside at that point. There's such a lack of heat at the outdoor air that it's very hard, based on the design of the system, to pick up heat to be able to transfer inside. Now, there are quite a few systems that can pick up heat even below 0 degrees, but a lot of times the cutoff point is -5. I think the best I've ever seen is maybe -20. I think I saw that on a spec sheet once, but don't quote me on it. -5 is a lot of mini splits, and high efficiency systems can get down to -5. But much below that, and you're not going to be transferring much heat from the outside to the inside. And it's basically a line, right? So the hotter it is outside, the more heat there is, the more BTUs that heat pump can put out. And then the colder it is outside, the less BTUs it can put out. So a 3-ton system, for instance, might be able to do 36,000 BTUs at 47 degrees, but only be able to do 15,000 BTUs at 0 degrees. So the amount of heat it can put out lowers as the outdoor temperature gets colder, and the colder the outdoor temperature is, the more heat we need to be able to put out, right? So there is a point at which the heat pump no longer is able to provide enough heat to keep the inside warm. And that point is called the balance point. Once you get past the balance point, that's when electric heat should come on, or in the case of dual fuel, when the furnace should come on and the heat pump should turn off. So every time a house is designed using a manual J calculation, you should be able to find the balance point and determine this is the point in time in which electric heat should be operated. or this is the point in time at which the dual fuel furnace can come on. And something that's never really done but is absolutely a good practice is if you got a heat pump, you find the balance point, and then you can set an outdoor thermostat to only allow the electric heat to come on once it gets below that temperature, and that'll save the most money on using a heat pump on a house, because you're locking out that electric heat until it's actually needed. On a dual fuel system, you have to do that. You either have to have a thermostat that's capable of knowing the outdoor temperature through a sensor or something, so that it can only operate one mode of heat where it's necessary, or you need to use an outdoor thermostat that will switch modes once it gets to that balance point. Okay, so that's what you're looking for on when a heat pump switches to the furnace or to the electric heat on a or on a dual fuel system. When you switch to furnace, and on electric heat, the point at which the electric heat should come on, and that is the balance point. All right. You should know how to troubleshoot a reversing valve. On reversing valves, there's a couple different things you need to do to troubleshoot them. Let me make sure. A, I know what answer they want, and B, I can explain to you guys a little bit more. Alright, so there's a few things that can go wrong with the balancing valve, okay? So, balancing valve, sorry, a reversing valve. There's a couple of different things that can go wrong. One is, think of a reversing valve as just a solenoid valve. That's the easiest way to picture it. Okay, so it's just a solenoid valve with 4 ports that switches the ports up. All right. If you're having issues with the reversing valve, there's a few things you can do to check it. Okay, number one, make sure you've got 24 volts or in the at the reversing valve. And if you're calling for heating, you might want to power the reversing valve on and off a couple times to make sure in cooling that it switches, that you get 24 volts to it. All right, so make sure you're getting proper voltage to the reversing valve coil first, whether that be 0 volts in heating generally or 24 volts in cooling generally. But like we said before, it could be the opposite. So that's the first thing you want to do, is verify proper voltage to it. If you're calling for heating, right, and or no, let's talk about cooling. If you're talking about cooling and the reversing valve should be on, then you check for 24 volts at the coil. If it's still operating in the wrong mode, or it doesn't seem to be operating properly, something else you can do, just so you guys know, alright, if it doesn't seem to be working, it's basically a piston inside of there, right, that moves back and forth to change the ports that get the refrigerant. So that if there's debris in the system, if good practices weren't used when the system was brazed or something like that, and there's for some reason some debris in that valve, it can get stuck. So you want to power the valve on and off, either switch modes quite a few times, or a lot of times what we'll do is put it in cooling and then kind of leave the spade connector off, and then kind of connect 24 volts, wait a second, remove 24 volts, wait a second, connect 24 volts, wait a second, remove 24 volts, wait a second. And that's going to try and free it up as it moves back and forth relatively rapidly, in case that piston is stuck. The other thing you can do is obviously ohm out the coil. You should probably do that before trying to free it, right? Your steps should probably be verify voltage, check the coil and make sure it ohms out, that it's not shorted or open. Okay, then if it's not shorted or open and the coil seems to be good, try and energize and de-energize the valve, and you usually can hear it click. So if you hear it clicking, then you know it's at least trying to move. So like I said, you can apply and remove voltage multiple times to try and free it up. And then the other thing to remember about troubleshooting reversing valves is that, and this is definitely in the materials that I gave you guys on troubleshooting refrigeration, a lot of times it can look like you have a bad compressor when you actually have a bad reversing valve. Okay, so the reversing valve will be bypassing hot gas on the discharge straight to the suction line of the compressor, because it's stuck in like a half position or something. And what that'll look like is a compressor that's not pumping. You'll hear the compressor running, but it won't seem to be getting a very big differential between the discharge side and the suction side. So if that's happening on a heat pump, on an AC system, it basically guarantees you got a bad compressor. Okay, compressor's no good. But or you've got some kind of other bypass there. If you've got some kind of hot gas bypass defrost or something like that, it could be a malfunction in that. But generally it's going to mean you have a bad compressor. But if it's on a heat pump, it could be a faulty compressor and it could be a faulty reversing valve. So before you condemn a compressor when you have a reversing valve, you want to verify that the reversing valve is operating properly. So if you think the reversing valve might be bypassing hot gas, if you look at my refrigeration troubleshooting guide that I put in there, it gives you a section for reversing valve bypassing hot gas to suction. And the telltale signs of that is low head pressure with high suction pressure and high superheat. And to diagnose it, you check the temperature difference between the suction line and the true suction line. So the true suction line, and I always forget this. Let me see if I can pull up a reversing valve diagram. Unless I'm staring at a reversing valve, I always forget which one's the true suction. But basically, whichever one is supposed to be the suction coming back from whichever one is the evaporator at that time, to I think it's the middle of the bottom. I'm pretty sure it's the true suction's the one by itself. But let me see if I should have a diagram somewhere. Anyway, I'll see if I can find that so I can make sure I tell you guys right. But you want to see if you got a temperature difference of less than 13 degrees. So if the temperature difference is less than 13 degrees between the two, then no. Let me state this right. You check the temperature difference between the true suction and the which is the suction that always goes to the compressor, and the suction line coming back from the system. If it is greater than 13 degrees, then if it's greater than 13 degrees, then the reversing valve is bypassing hot gas. If it's less than 13 degrees, it's not bypassing hot gas. Now, I will tell you this changes from manufacturer to manufacturer. They'll give you different numbers. I've seen 3 degrees, which is ridiculous. I've seen 5 degrees, I've seen 8 degrees, and I've seen 13, which is why I use 13, because 13 is a good guaranteed number. You really shouldn't have too much of a difference, but you will pick up heat because the suction line inside that reversing valve is so close to your discharge line. They're all moving through a valve that's the same proximity, you know what I mean? You're gonna pick up some heat as the suction gas moves through the valve because it's right next to a really hot refrigerant line. So there will be some heat transfer there, but it shouldn't be a whole lot. And ideally, it would be only a couple degrees, but 13 degrees, if you see that, that's guaranteed. And I would say if you're getting to about 8, I would be concerned. But if you see more than 13, guaranteed, condemn the valve and you need a new reversing valve. Alright, you can try and unstick the valve if it's just stuck at a half position, but if you can't do that, then you need to condemn the reversing valve. So just to recap, if you think there's something wrong with the reversing valve, check for proper voltage, for the mode that you're in. Check the coil to make sure that the coil operates properly. Listen for a click, because that's a sign that it's trying to move or it is moving. When you apply power and remove power, you can apply power and remove power multiple times to try and get it to unstick. And you can check the temperature across the suction line and the true suction line to verify that you don't have too much of a temperature difference. And the last thing is, if you need to and the valve's stuck, you can try lightly tapping on it with like a rubber mallet or something. But remember, there's a piston and a reversing valve is usually copper. So if you hit it too hard and you dent it, it's going to kill the reversing valve, right? You put just a little dent in that copper on the valve body and you're going to mess up the reversing valve. So if you're going to tap it to try and get it to move, do so with extreme caution. Usually I find that if it's sticking a little bit, putting power on and off the valve will usually unstick it. I've never had to try and tap it, but it is one option that you'll find in textbooks and stuff. Alright, if a compressor is not operating, you should know how to troubleshoot a compressor. So if a compressor is not operating, you need to, of course, verify voltage first, right? Verify you got proper voltage to the compressor. Check. We talked about how to troubleshoot PSC motors. If it's a permanent split capacitor compressor, you can ohm out the windings. If it's a three-phase compressor, same thing, but obviously with a PSC, the readings you'll get is different than a three-phase. But either way, check the windings and make sure you're getting proper resistance, or what appears to be proper resistance on all three windings. Nothing's open, or the overload's not open, or something like that. And then remember that if everything doesn't check out at the wires at the contactor like we talked about in the lab, then make sure that you actually go to the head of the compressor and check everything there. Take the connectors off. If at all possible, verify you're getting voltage at the actual connectors with you trying to run power, and do so very carefully, and actually ohm out the windings at the compressor itself. Those are the first things you'll do. If it's still not operating but all those things seem to be fine, the best thing to do is give this compressor some time to cool off, because it's probably overheating. That may be 5 minutes, that could be a few hours, but give the compressor time to cool down in case the overload's opening. Alright, double check that the windings are good, then take your amp meter and put it around the wires near the compressor contactor and measure the amperage and stick it on maximum or something, so that you can see the max amperage it's pulling. A lot of times if it electrically checks out but it's still not operating, it's locked up and it's pulling so much amperage that it's opening the overload for a short period of time, and then it closes again. And then it tries to start up, it locks up, and then it opens the overload because the windings are getting too hot as it's trying to turn on. If you're seeing a high spike in amperage and then the amperage goes to nothing, then it means the overload's opening on you. If that is what's happening, then what you want to do is try a start capacitor if there isn't one, or verify that the start capacitor is good and the relay for the start capacitor is good. Try that and see if the compressor will come on with either a new start capacitor and relay, or like one of those little super boosts or something like that. See if it'll come on then. If it still won't come on after trying that, you can try to double up a start capacitor. So use two start capacitors at the same time, so you get double the capacitance, but you need to make sure that they come out of the circuit fast. But you can try that for a second with 2 start capacitors, and sometimes that'll jump start the compressor. Basically, it gives it a bunch of juice, but you never want to leave it with both start capacitors in. If after you get it running using 2 start capacitors, it still doesn't operate using just one. So if you get it jumped with 2 start capacitors and you take the second one out and then you put it on one, it doesn't start back up, then don't bother. But if it does start up and then it'll continue to run after that with 1 start capacitor, it might have just been a little bit locked up and it'll continue to run. Now, if you've got to do that, it does mean that you're probably going to have a compressor failure pretty soon. Okay, it could be a day, it could be a year, but it definitely means that something's locking up in the compressor, and it may not continue running for a very long time. So that's just something to keep in mind. But of course, the first thing you do if it's not operating in cooling mode is verify that your compressor is getting voltage and that the windings are good. Everybody knows what the thermostat wire colors are, I hope. Your wire colors for a thermostat are red, R, is 24 volts. C, which is usually blue or black, is common 24 volts. Y is your outdoor contactor. G is your indoor fan. W is electric heat or your furnace heat. O is your reversing valve. And then sometimes brown or black is emergency heat if it's got an emergency heat terminal. That's usually a redundant terminal, but you can have that for that. And those are your colors. So the biggest ones, those are the biggest ones to remember. Everything else, Y2 and things like that, you can basically pick any color. Everybody does them a little different, but those are the standards. So R is 24 volts hot, C is 24 volts common, Y is outdoor contactor, O is your reversing valve, G is your fan, W is heat or auxiliary heat. If you're trying to troubleshoot a thermostat, alright, and it's not operating properly, you can jump the terminals, okay? Old thermostats used to have what they call a sub base. I mean, I guess technically you still have a sub base on thermostats where you connect the wires together. Yeah, you could still call it a sub base. I don't think about it as a sub base. I think about the old Honeywell thermostats as having a sub base, but you still have a base for the thermostat where all your wires connect before you put it on the wall, right? So if you think you're having an issue and you think it's the thermostat, which is actually pretty rare, but thermostats can fail, what you want to do is take the thermostat off the wall and then jump the wires as if you're making the thermostat switch, right? So if you're trying to call for cooling, you jump R to Y at the thermostat and see if everything works. R to G to run the indoor fan, see if everything works. R to W for heat, see if everything works, and so on and so forth. And remember, with a heat pump, you're going to have to power O if you want cooling on, right? But you can place the jumpers at that sub base, and what that does is that tells you, okay, I'm getting power from R to the thermostat sub base, and then it's going to whatever I'm trying to test and getting back to the indoor unit. And if everything operates by jumping it, but it doesn't operate when you put the thermostat on, you know the thermostat's not operating properly. So if you jump R to Y, the outdoor unit will come on, right? The compressor contactor will come on. If you jump R to G, the indoor fan will come on. If you jump R to W, the electric heat or the furnace will come on, so on and so forth. So just remember that that's a good method of testing it, and those are the things that are energized. But remember what your terminals are that we just talked about, and remember that you can jump them over to energize those things at the thermostat sub base. Thermistors. troubleshooting thermistors becomes more and more important every day because a lot of things, a lot of high efficiency equipment has thermistors in it. A lot of newer defrost controls have thermistors in them. And all the thermistor is a device that changes resistance based on its temperature. That's all it is. So the resistance inside the thermistor will be different based on whatever temperature that thermistor is. So on a positive temperature coefficient thermistor, as the temperature goes up, the resistance goes up. On a negative temperature coefficient resistor, as the temperature goes up, the resistance goes down. So there's two primary types, positive temperature coefficient and negative temperature coefficient. And positive means they go the same, resistance goes up with temperature. Negative means resistance goes down with temperature going up. But that's all it is. It's a device that changes resistance based on temperature. There's two ways of troubleshooting them. Generally, how they work on a system, okay? Generally, how a thermistor is used is that a circuit board will send 5 volts. It could be a different voltage, but it's usually 5 volts. Most circuit boards actually operate at 5 volts DC. No matter what the incoming voltage is, the rest of that board operates at 5 volts. That's very common. It could be 10, it could be 12, but 5 volts has become extremely common. And for a lot of things, 3 volts is becoming pretty common, but not quite with the stuff we do yet. Alright? Anyway, generally what the board is going to do is it's going to send 5 volts to the thermistor, and then that thermistor is going to go through the 5 volts is going to go through the resistor that is the thermistor, right? And then come back to the board, and the board will monitor the voltage coming back. If you're sending 5 volts to the thermistor, and it's a let me see if I can come up with a good example here. Remember Ohm's law, right? So Ohm's law, E equals I over R. No, yeah, E equals I. I can draw it, but I can't say it right. E equals I times R, right? To get your voltage, it's resistance times amperage. To get your amperage, it's voltage divided by resistance. And then to get your resistance, it's voltage divided by amperage, right? So hopefully you guys know Ohm's law pretty good. If not, make sure you know Ohm's law, because it's very good for troubleshooting things like this, right? So you can figure out one or the other. So for instance, if you got, like I said, a 5 volt if you got a 5 volt signal and the thermistor is at, say, 20 or 200 ohms, let's just say 200 ohms. I don't know if that would be a common number or not for resistor, but well, no, we want to do a voltage drop. What am I saying? Forget it. The point is it should be divided resistance, so the voltage is going to drop divided by the resistance, right? No, you gotta, to do a voltage drop, you have to multiply it back or something. It's been a long time since I've done calculating a voltage drop. But anyway, the voltage will drop through the resistor, right? So, you know, to just make up some numbers real fast so you understand, you know, if that resistor's at 200 ohms or something, then the voltage might go from 5 to 4 volts. And then if it's at 1,000 ohms, it might go 5 to 3.5 volts or something like that, right? I probably need to come up with an example for that, but that's the basics, right? So since you have a reduced voltage coming back to the board, that board will see that reduced voltage and understand that the temperature has changed. Okay? So what you can do to test the thermistor is check the voltage before it and check the voltage after it. And if you're not dumb like me and you remember how to calculate your voltage drop, then you can figure out what the resistance is based on how much the voltage dropped, okay? Otherwise, you can just take the thermistor out of the circuit and measure the resistance. And what you'll usually do is you'll just pull the thermistor, take it out of the circuit, and then to make sure it's good, first you'll make sure it's not open or shorted, right? So you shouldn't have 0 ohms and you shouldn't have infinity ohms. You should have something in between. Usually, if a thermistor's bad, it's opened or shorted, so you'll get one of those. But if you don't get either, but you think the thermistor really isn't working right, you can stick the thermistor in a glass of ice water, which should be 32 degrees, right? And measure the resistance, and then find the chart for that thermistor and make sure that the resistance you get is what it's supposed to be at 32 degrees. And if it's not extremely close to that, then the thermistor, something's wrong with it, and it's reading temperature wrong. So that is kind of the easier way to do it. I don't think I've ever actually had to calculate voltage drop across it to test it. I don't think I've ever had a thermistor that wasn't just opened or shorted. But if you do, if you think it's just poorly calibrated or a bunk thermistor straight from the factory, you can verify that using voltage or calculating your voltage drop and checking the voltage across it, or by just sticking in some ice water and comparing the resistance, which is generally what they recommend. They usually don't try and get you to do it based on voltage drop. But there has been a couple times I've been troubleshooting a board and had to see what the voltage was there to verify operation. So, sorry for my lack of memory there. I'll go back tonight and try and remember how to calculate voltage drop just so I don't mess that one up again. All right. Now there's a couple. All right. So in heat pumps, right, we have 2 metering devices. We have a metering device inside and we have a metering device outside, right? On most systems today where you'll have 2 TXVs, the TXVs have check valves built into them, where if the refrigerant's going one direction, it'll go through the metering device, and in the other metering device, it'll just bypass it basically. And then, when it switches modes, those two will operate differently. So basically, there's a check valve built in to make sure that the refrigerant flows in the right direction. If it doesn't have that and it actually has external check valves, there'll be a pipe that goes around the metering device with the check valve in it to make sure that the refrigerant is only going in the direction it's supposed to. So, if it's in cooling mode, it'll go around the check valve in the outdoor unit and through the metering device on the indoor unit. If it's in heating mode, it'll go around the metering device in the indoor unit and through the metering device on the outdoor unit. Okay? There are a lot of systems that have those check valves in them still. Okay? So you'll know it's got a check valve when you see a pipe that goes around your TXV or around your piston. If you've got a pipe that goes around that metering device, there's a check valve in that pipe. And usually it just looks like a slightly bigger section of copper pipe. They're usually spun closed copper check valves. All right? If there is a check valve that's not closing properly, okay, then you'll get a low pressure differential across the valve, okay? So normally your pressure drops significantly, right? The pressure is going to drop significantly across a metering device. But if it is if it is 13. Yeah. If it is, where was I going? Correct. All right. Anyway, if the check valve is not operating right in either mode, you'll have a low pressure differential, right? Because it's like your metering device isn't there. So, if your high side's supposed to be 300 and your low side should be about 100, on our imaginary refrigerant, then if the check valve's leaking by in either mode, you might have, 225 on one side and 175 on the other. You've got a very low pressure differential. You got a low compression ratio. That's kind of your first clue. All right. The other thing is the coil temperatures will be out of whack and you won't have good subcooling or good superheat either way. So you'll have a low pressure differential, you'll have low subcooling, you'll have low superheat, and all in all, it'll tend to look like a bad compressor. Another situation that could look like a bad compressor, right? And generally, you might see some frosting around that check valve because a lot of times it won't operate. It won't be open like all the way. It'll just be leaking by. So as the refrigerant gets partially metered through the check valve, you'll see some frosting on the other side of the check valve because refrigerant's escaping by. So those are a couple signs you can look for. But in cooling mode, if the check valve's leaking if the leaking check valve is on the indoor unit, right? If the leaking check valve is on the outdoor unit, but it's in cooling, you won't really know it's got a leaking check valve, right? And if the leaking check valve is on the indoor unit in heating, you won't know if you got a leaking check valve because it's leaking the right direction. But you have to switch modes to see which one it is, right? So that's kind of what they'll ask you on your test is, which way does it have to be to see if it's leaking? If it's, in the right mode, you won't know you have a leaking check valve until you switch modes. Okay? So the check valve should be open on the outdoor unit in cooling, and it should be open on the indoor unit in heating. It should always be closed for the opposite mode. All right. Next one. What the heck? All right, so there is a question on your exam. I'm just going to tell you guys to do this on this one. There is a question on your exam involving solenoid valves. What I'm going to tell you to do for this one is simply read section 3.4.1 about solenoid valves, and maybe one of you guys can explain to me whatever they're talking about on these solenoid valves. There's a few different types of solenoid valves. You have pilot operated valves and direct acting valves. I know that. Most are going to be pilot operated, which means if you don't have a good pressure differential in the system, they won't work properly. A reversing valve is often a pilot operated valve, and basically what that means is you use the pressure of the refrigerant to actually open and close the valve, which is why they won't operate right if you don't have a bit of a differential. Okay? So if you have a very low pressure in the system, solenoid valves often will not work. Reversing valves often will not work. Generally you're going to be looking at a system that's near flat anyway, so the solenoid valve not operating is probably not what you're troubleshooting for. But if for some reason you are, and the solenoid valve doesn't seem to be working, maybe make sure you have enough refrigerant. But a pilot operated valve, basically you open and close a little extra, you open and close a port, right? so that that port will allow for refrigerant to go in a particular direction, and that refrigerant going in the direction is actually what closes and opens the valve, and that's a very common type of solenoid valve. A direct acting valve is going to have to close and open against the pressure of the whole refrigerant, which can be very high, especially something like 410A. It's going to be a very high pressure that that valve has to overcome. So you're going to run into issues with needing to be able to draw a lot of power to open and close that valve. And I think that's part of what they're talking about on that question, but read section 3.4.1 about solenoid valves and make sure you understand that. And then the last question on your test is about different durations of defrost mode. So remember, I told you after 30 to 90 minutes you're going to enter defrost mode because of time. Okay, so you don't want a system, especially when it's very cold outside. If you just let defrost happen anytime that the defrost thermostat says the coil is cold, then you could be going into defrost like every 5 minutes. Because, if it's below about 45 degrees outside, somewhere around there, the coil is always going to be below freezing, because you have to be colder. The refrigerant coil outside to pick up heat from the outside has to be colder than it is outside, right? If we're going to pick up heat from something, we need to be colder than where we're trying to pick up heat from. So if it's cold outside, the coil is always going to be even colder. So if we just let defrost get controlled by the coil temperature, then the system would stay in defrost forever when it gets, like I said, about below 45 or so. So instead of running defrost all the damn time, what we do is say, okay, we want to run it until it starting to ice up, and then once it's starting to ice up, we want to go into defrost. So if it's very humid outside or it's raining or something, you really need to defrost more than if it's pretty dry air outside. And in the winter, it's often pretty humid outside, actually. The reason it stays dry inside is because as we heat the air, we lose relative humidity. But it can be pretty humid outside in the winter. So depending on your environment, you'll want to set the defrost to either 30, 60, or 90 minutes. But if there's a lot of rain and stuff, ideally you would change the defrost interval based on how wet it is outside. Now, that's usually not feasible. There are systems like trains that have demand defrost, so the system does a good job of detecting how long it takes for the coil to frost up, but commonly you just have to pick something. If you're in an area that gets a lot of rain during the winter, then you'll want to set the defrost lower than if it doesn't. And if the outdoor unit doesn't really, if it's got some kind of cover over it or something, something above it that keeps the rain from going on the top of the outdoor unit or hitting the outdoor unit, then you can probably leave your defrost at 90 minutes, right? But if not, then you're probably going to want to pick something like 30 or 60. But just remember that the wetter it is outside, the more you need to go into defrost. And typically you're going to go into defrost every 30, 60, or 90 minutes. And the wetter it is, closer to 30 you want to be. The hotter, the drier it is, the closer you want to be to 90 minutes. And you got to make a judgment call on it. There's a few factors that affect it. One is how wet the environment is. Two is how much sun hits the unit, right? Because the sun will help keep it from frosting up as quickly. So if the unit gets a lot of direct sunlight, you might be able to go closer to 90 minutes. If it doesn't get any direct sunlight, you're going to want to go closer to 30 minutes. And basically what you really want to do is do as much as you can to monitor the system and see how often it gets frosty and try and keep it from developing a lot of frost as much as possible. A little bit of frosting's okay, but if it starts to restrict airflow, that's a problem. So anytime it looks like the defrost isn't doing a good job of keeping the unit from getting iced up, then you want to lower the interval of defrost. Make sense? And with that, we have covered every question that is on your heat pump exam. Alright, let's try and run through these PowerPoints real quick so we stay on schedule here. I didn't think it'd take quite that long to go through all those, but since we did, let's try and go through this. Let me go ahead. I will share the screen and let's run through at least one of these PowerPoints, and hopefully two. Alright, share screen. Where is it? Huh. I can't, I'm not sure which one it is. I guess try this. Can you guys see the PowerPoint? Still see it? Alright. So this PowerPoint's on gas furnaces. So let's talk about gas furnaces real quick. When you've completed this lesson, you should be able to do the following. Describe how to troubleshoot the components related to gas heating. Describe the control circuits and the typical sequence of operation of various gas heating units. Describe the operation and troubleshooting process for thermocouples. Describe the operation and troubleshooting process for ignition devices. Describe the operation and troubleshooting process for flame sensors, and identify common problems associated with system airflow. Using the proper tools, instruments, and control circuit diagrams, isolate and correct malfunctions in the gas heating system. Alright, hot surface igniters, including nitride. You have silicon nitride and silicon carbide hot surface igniters, okay? So hot surface igniters, including nitride devices, are by far the most popular now in residential furnaces. Alright, and there's some pictures of various hot surface igniters. Or various ignition systems, right? So this first one here is gas spark ignition, which is pretty common. You'll see it often on, again, ring units, on residential, and a lot of commercial units will have gas spark ignition. So the most common type nowadays with that is intermittent ignition, right? So the pilot only comes on right before the main burner comes on. So the control will start sparking the igniter, let the pilot gas flow. The gas will ignite the spark igniter will ignite the gas. Then the flame sensor will see that the pilot is on, right? The pilot will be proved to be on through the flame sensor, and then main gas goes on and the pilot goes out. Alright, that's more efficient than having a standing pilot all the time. So that is actually probably the safest way to prove ignition. It's better than a hot surface igniter, but it's not so much of a difference that anybody really cares. But having a flame to light the gas is always the most guaranteed way to light the gas. So really the best way is kind of intermittent spark ignition, but it's more complicated than a hot surface igniter, so we usually use hot surface igniters. Glow coils, basically think of glow plugs on diesel. That's pretty much obsolete now. Nobody does that anymore. A regular pilot, so that a pilot stays on all the time, and that's usually flame sensed through a thermocouple instead of a flame sensor. If you have a standing pilot, a thermocouple is generally used to prove that the pilot is staying on. And then hot surface igniters, This is a flame sensor, so that's what proves flame, and then another type of igniter, which is nitride. This is a carbide one, I think. This is a nitride. The nitride ones are kind of smoother. They're both really common. Nitrides are getting more common than carbides, but really basically the same. Alright, you have a circuit board. You pretty much always have a circuit board on gas furnaces these days, because using regular controls and relays to use this to verify the sequence of operation for gas equipment is relatively complicated. It's way easier to do with a microprocessor, so most gas equipment is going to actually have a circuit board now. Older equipment didn't have it. There are ways to do every step in that sequence without a circuit board, but it's way more complicated than just using a circuit board. Alright, and these things are almost universal. A circuit board that works on a hot surface igniter can work in almost any furnace, and a circuit board that uses hot surface igniters and a circuit board that does spark ignition can work in just about any furnace that uses spark ignition. The main difference between them is what wires go where. Okay, you could take a universal board and replace almost any hot surface ignition or spark ignition board in it. But of course, it's easier to use the one that came with the equipment. And if it's more complicated than the basic sequence of operation, obviously you'll need that particular board. But they all operate very, very close to the same. Here is a diagram of a furnace wiring. We're not going to go through this very much, but this would be a typical furnace wiring diagram, and I would encourage you to look through that. Hopefully we'll go over wiring diagrams some other time and we can talk about them, but that's what you got. Alright, electronic gas furnace controllers. Again, most of them are going to have boards. All the boards are very similar. They may look different, but they operate almost exactly the same. Electronic gas furnace controllers have diagnostic aids built in to assist the troubleshooting process. So this particular one, these are common diagnostic codes, right? You have system lockouts, so it locked out because it tried to light too many times and it didn't work. The pressure switch is stuck closed. The pressure switch is stuck open. A high limit switch or a flame rollout. A 115 volt power reversed or an improper ground, and a low flame sense signal. The most interesting one here is the power reversed. You have to have a lot of things, right? It doesn't matter which one's hot and which one's neutral, okay? Most motors, if you hook up the wires opposite, it doesn't make a difference. It'll still run, and usually it'll run in the same direction. But there are certain boards and things like that that need to have the correct polarity, and furnaces are always one of them. Primarily, I believe, because of the flame sensor, because the flame sensor senses the signal through ground. That board has to be hooked up in the correct polarity or it won't work right. So there's almost always a code that says, hey, your polarity is reversed. Or if the board doesn't seem to be working right at all and it's brand new, try switching the polarity. Maybe the wires are hooked up wrong. So just because, black is supposed to be hot and white's supposed to be common, doesn't mean that somebody didn't accidentally reverse the wires somewhere in the electrical circuit, okay? So if a furnace isn't working right and there is no you just started it up, because generally this is going to be when you first started up or an electrician did some work or something like that. If it's not operating right, you want to verify polarity of the power coming in, because it has to be black to black, white to white, and black has to be hot and white has to be neutral. If it's not like that, you need to reverse black and white so that the polarity is right. It's a diagram for a natural draft package unit. Not super common. Most everything's going to be induced draft. Condensing furnaces. So a condensing furnace can extract the heat from the flue gases, neutralizing the resulting acidic condensate may be required by code. Low return air temperatures can also create problems. So a a condensing furnace has two heat exchangers. You have the primary heat exchanger, which is the same as every heat exchanger in every furnace, basically, right? Then you have a secondary heat exchanger where the condensate and the flue gas goes through to extract more heat out of it. Typically, this is going to require a stainless steel or a PVC vent because the condensing flue gas will corrode steel, right? It's going to eat through the steel pipe. So the telltale sign that you have a condensing furnace is going to be the PVC or stainless steel piping coming out of it, and you're going to have two heat exchangers, a primary and a secondary heat exchanger, and they will need a condensate drain in heating. Alright. Here's a gas-fired boiler wiring diagram. Typically, gas-fired boilers are going to have the same sequence as any gas furnace, but I will say boilers seem to more commonly be either a standing pilot or an intermittent spark ignition. Hot surface igniters are slightly less common, but it could be any of those three. It doesn't really matter. Every boiler is kind of its own animal, but they're generally extremely simple. Testing a thermocouple. So if you think you've got a bad thermocouple, remember a thermocouple is going to be on a standing pilot. So the most common thing you'll troubleshoot a thermocouple on is a water heater or a boiler. But water heaters are extremely common. A regular gas water heater is about 60% efficient, and it generally uses a standard pilot on the burner system. So if you have a standing pilot, then you generally will have a thermocouple to prove, or it can also be called a thermal pile if it's a little bit bigger. That proves that the flame's on. And how a thermocouple works is it's a bimetal, it's a two dissimilar metals inside a rod, right? And when it's heated up by the flame, those two dissimilar metals produce a voltage, all right? A millivolts voltage through it, and that is what holds the gas valve open. So you're actually using the fire to create a voltage in two similar metals, and that's what allows the gas valve to stay open. Alright, so if you're trying to troubleshoot one, this is a good picture here of what you do. You need to hold the pilot knob down, right, to keep the flame on. Then you have to hook up your meter from the tip, right, the tip of the thermocouple that screws into the gas valve to the copper part of the thermocouple going down. So this is hot basically, and this is ground. Alright, and you read the voltage in millivolts AC, right, millivolts. Might be DC, whatever. It's usually the only millivolts you have on your meter anyway. You need a meter that has a millivolt setting, and you need to check it from the tip to ground. And you should have generally 20 to 30 millivolts, but thermal piles can be more. If you run across a thermal pile, sometimes those are 20 to 300 or 200 to 300 millivolts. But you want to know on a regular thermocouple it's going to be 20 to 30. On something that has a thermal pile, you might want to know what the manufacturer calls for as far as millivoltage. But you'll just check that. Now, if you don't have three hands, right? Because this kind of takes three hands unless you got the clips on your meter, because you got to hold it here, and hold it over there. They do actually make adapters that you can screw in to the thermocouple to allow you to check voltage with it being in place. They do make adapters for that, and it's kind of nice to have around. But if you use that adapter, typically you're going to see a smaller voltage. So my advice is read the instructions that come with that adapter to make sure you know what you're going to read. If I remember right, the voltage on one of those, I think you're going to read 10 to 15 volts normally when you use one of those adapters. But it's been 10 to 12 years since I've used one. But anyway, that's how you properly diagnose a thermocouple. I can tell you real world, basically, if you light the pilot, and you hold that knob down for about 30 seconds, and then you let go and the pilot immediately goes out, your thermocouple is bad. That's why I haven't used one of those adapters in years, because you kind of get good at just saying, nah, the thermocouple is no good. And if you're wrong, it costs you $12, and you have to, you have to bite the bullet and say you were wrong and it was actually the gas valve. But 9.5 times, if not 9.9 times out of 10, if the pilot won't stay lit after the thermocouple's had plenty of time to heat up, then it's the thermocouple that's bad. Oh yeah, look, they got under load here. At least 10 millivolts under load. There you go. I remembered halfway right. 10 to 15 millivolts. So yeah, if you have an adapter, you can use that to test a thermocouple under load. Hot surface igniters. To test a hot surface igniter, you want to ohm out the hot surface igniter and check the resistance across it. Best thing really to do is look up what that specific manufacturer calls for resistance across it and see if it's right. Usually if a hot surface igniter is bad, it's open, right? It's got a crack in it. But you can diagnose a hot surface igniter that's failing, that's starting to fail, by seeing an abnormally high resistance, or an abnormally low resistance for that matter, but generally the resistance starts to go up, if I remember right, as they age. But you want to look up what the that particular hot surface igniter, what its normal resistance range is, and if it's outside of that range, then you'll want to replace it. But if it's bad, usually it's cracked, so you'll have infinite resistance. On a flame sensor is a little different than a thermocouple. A flame sensor is definitely something that you'll want to diagnose with the meter when at all possible, because it's pretty common for the issue to not be the flame sensor and to actually be a ground or a board or something like that. I gotta say, it's usually, if a flame sensor's dirty, then that's all your problem is. You can clean it off with some light sandpaper or something and get it working. But if that doesn't do it, if cleaning the flame sensor doesn't fix it, then you really want to check the signal from the flame sensor to the system, because it could be that something's wrong with the board, or it could be that you just don't have a good ground with the flame sensor. It could be any number of things. But if you're getting proper microamps from a flame sensor, then you need to look elsewhere than the flame sensor. And it's very important to do that, because you will run into weird situations with bad circuit boards and stuff where this doesn't work, because a flame sensor puts out a very small amperage. You measure the signal in microamps, okay? Millionths of an amp, to verify the flame signal, and that's such a small reading that any problems in that flame sensor circuit can make it not work properly. So generally a flame sensor, if you clean it, it'll work just fine, but if it doesn't, then you need to verify whether the issue is the flame sensor or something else. So the normal range is 0.5 to 4.5 microamps, okay? And you test that in line. So if you've never checked amperage without using an amp clamp, but by checking it through the meter, this is how you check amperage through a meter. You put it in series with the load, right? So one tip is going to be touching your flame sensor, then it goes through the meter, goes out of the meter, and goes to where what's supposed to be connected to the flame sensor, the lead that's supposed to be connected to the flame sensor. You disconnect that and run the signal through your meter. And you should be looking for 0.5 to 4.5 microamps, all right, which is looks like a little U and then an A. That's microamps, all right. And that's definitely something you want to be in the habit of checking if you're having an issue with when a flame sensor is bad. Generally what's going to happen is the main burner will come on, or the pilot will come on for a few seconds, and then it'll shut right off because it didn't detect a flame signal. And it'll do that 3 times and then lock out. And if it does that, If everything seems to work, the burner comes on, then it cuts off after a couple seconds, it's either a dirty flame sensor or something wrong with that flame sensing circuit, and that's how you troubleshoot it. Every meter can't perform that test because if you don't have microamps, then it's not going to work. Wait, no, they're not even talking about a flame sensor test anymore. What is this? Flame sensor troubleshooting. What the hell are they doing? I don't know what this is. I've never seen any relay that you're testing in this momentary switch. I don't know. Alright, ignore that because I have no idea what they're trying to do there. Alright, 3 kinds of problems are typical with airflow related problems. Obstructed airflow, which is dirty air filter or fouled indoor coil. Ductwork, sizing, or poor design. Undersized ductwork is extremely common. Blower motor, cleanliness of the wheel, speed setting, or difficulty starting. Those are the typical things that you're going to find affect airflow. Which component on the control board controls blower speed in the heating and cooling modes? The indoor draft inducer runs and the igniter energizes, but the gas valve does not energize. What should you do? Replace the gas valve, replace the control board, check to see if 24 volts is available at the gas valve, or check to see if there's a call for heat signal from the room thermostat. The answer there would be check to see if 24 volts is available at the gas valve, because the draft motor comes on, the pressure switch closes, then the hot surface igniter energizes, then the gas valve should come on. If the gas valve does not come on, you're going to want to check to see if there's 24 volts at the gas valve. If you do have 24 volts at the gas valve, you'll want to double check your connections and check the coil of the gas valve, but odds are if you have 24 volts at the gas valve but the valve does not come on, then the gas valve is bad. You will have to replace it. But first, make sure that there's 24 volts at the gas valve. Alright, and that is class. We're going to stop there. Does anybody